Hello, Professor. I hope you're having a great day. My name is Hong Anh, and in today's presentation, I'm going to talk about what I implemented in homework 17 to homework 20. So here are my table of contents, which I will present one by one, each from homework 17 to homework 20. And in this homework, my personal goal is to understand how linear algebra, data preprocessing, and neural architectures connect. So the thing about homework 17 is that I understand that it can be implemented using codes, Python codes, but I really wanted to do a manual version, even though it takes time, to actually perform principal component analysis, or we say PCA, on your dataset that you gave us. And I verified the results using the matrix algebra without relying on built-in PCA functions that you gave in the implementation recipe. Even though I'm not quite sure that my computation is totally correct, but I applied the theory on eigenvectors and eigenvalues to compute this. And later on in my second version, I did a code version in which I implemented Python codes to check my manual version results. And the final goal here was to show how PCA can identify direction of maximum variance in the data. So with homework 17, we had a 3x3 data matrix was used as an input, and I did the step of mean centering in which I calculated the mean of each variable and subtracted it from every observation to get the centered metric. And the third step is about computing the covariance matrix, in which I computed manually to measure variable relationships. And about the SVD decomposition, I applied singular value decomposition and also squared singular values divided by n minus 1, and it gave the eigenvalues of the covariance matrix. So that was a brief overview of what I did in my manual version. A clearer um, version will be shown in the file that I submitted in the form of homework 17. So I wanted to talk about the results that I received from computing PCA manually, and I interpreted the result and I put it in the table on the right here. And the thing I interpreted about the result is that the PCA reduced data from 3D to 2D while preserving 100% of variance, and also verified the orthogonality of eigenvectors, in which I computed in homework 17, and it did some reconstruction. And we can tell from the plots that the two first PCs captures nearly overruns, and it shows that it's a effective dimension reduction. And it also revealed that the dataset lies in nearly like a plane, which is a third dimension redundant, and the transformation relates features and simplifies structures for analysis. So as I said, I did two versions, and in this code version, I implement the same PCA procedure from homework 17 using Python and the library of NumPy, and in order to verify that the computational results match the hand calculated values, and the results I received that it matched, and the NumPy all close confirm that reconstructions is 100% accurate, and we can tell that covariance in the PCA basis was diagonal and they have no correlation. And in this code version, I was able to visual plot, and it showed rotated data axis aligned with the PCs, in which I will briefly explain in the next slide. So here are the plots that was visualized using the Python code, and it shows that how PCA transformed the data. And in the original plot, the points follow a diagonal line indicating a strong correlation between variables. And after applying PCA, the transform plot showed the same data rotated, so the new axis, which is the principal components, are perpendicular and uncorrelated. And most of the variant now lies in the first principal component PC1, and it confirms that PCA effectively reduces redundancy and also captures the main structure of the data in fewer dimensions. So moving on to homework 18. So in this homework 18, we were asked to implement a code using the reference from Kaggle. And I can tell that the goal is to predict treating pressure NOR from the industrial sensor data that you gave us by cleaning features, diagnosing multi-collinearity, and comparing regression models to find the most accurate and stable risk approach. And here are the steps that I have implemented, starting from loading the data as usual. And I also did two versions. One version with the heat maps where I drop row with null target and remove constant columns. But I also did a heat map that I did not drop any um, null values or constant columns. So you can observe it in my full version of Homework 18. And I also built four correlation heat maps, like two on clean data and two on raw data, to see how nulls and constant distort correlation, as I've said before. And I also computed features, target correlation, and VIF to detect multicollinearity. And after that, I received the notable features by correlation, which are the top example I used for analysts. So the following slides are the models that I have trained. Because when I crop out the image to put on the slide, the quality isn't so good, so I only put some significant models here. For further details, you can refer to my Homework 18 PDF file. So in this slides, I'd form a table in which I will evaluate all of the models. And from this table and from what I've observed in the file, I can tell that the random forest and the RFE is the best model performer because it gives us the high accuracy and stable generalization, and also compact features subset improves reliability. The following performers are listed, which is the random forest after VIF dropped. Moving on to the decision tree, the rich would be the baseline. And in all of the models that I have evaluated, the tune rich, in which I refer to the Kaggle codes. I did that, and I can tell that it's extremely unstable and overfitted, and it came to a conclusion that it's unsuitable for this dataset. So, in conclusion, the heat maps show how cleaning, like dropping nulls in constant columns, clarifies true feature relationship, while raw data can mask them. About the model evaluation plots, which is the most important part, we can tell that regression scatters and the model score bar chart illustrate prediction quality and make it clear that the random forest with RFE provides starter fits, which are points closer to diagonal, and the highest cross validated R squared among tested models. And personally, I think that I could have done better with Homework 18 by tuning the hyperparameter for random forests, like tree, depth, or min samples, with CB green and random search. And I would have tried gradient boosting, which implemented the SGBoost model for potentially higher accuracy, but I haven't really referred to any um, example yet, so I decided to go with what I'm familiar with. So moving on to homework 19 and 20, I and understand that homework 19 is in manual version, and in homework 20 it's implementation of the homework 19. And the two homework are done in the same six steps, in which I built both Hamming and Hopfield networks, and also use small binary vectors as training patterns and stimulated noise and partial inputs to test recall capability. And after that, I verified the networks to how it converged to the correct stored pattern, but through different mechanism. And Hamming and Hoffield have different mechanism. And I also compared the stability, recall accuracy, and noise tolerance. And I also discussed how increasing stored patterns leads to interference and misclassification in the Hoffield networks. So, this is the result table. We have three networks, including Hamming, Hopfield, and the Hopfield with overloaded storage test. And from what can be interpreted, the Hamming network has the correctly recognized the nearest stored patterns, and it was update 1 to 2 steps, which is the easiest, and it was a fast convergence output, and the output stabilized immediately and works well for pattern matching. And the rest are what I have tested but not included in my code file, because I personally think that it could be more time saving, but I also listed the result of it on here. So moving on to what I did with the code implementation, I followed the exact same steps as the manual version by building a two-layer perceptron using hard limbs to classify points based on two linear inequalities, and it correctly separated points inside or outside the defined regions. And I also implemented a two-layer threshold network, and it successfully classified points by quadrant using the hierarchical neuronal layers. And with the Hamming networks on problem B, it created similarity and WTA layers with porcelain activation to recognize binary patterns and correctly identified the matching prototype. And in homework 20, which is a code implementation of homework 19, I basically did the same stuff. And about the third problem in homework 19, in this I computed symmetric Hebbian weight matrix for associative memory and also stored three binary patterns for recall testing. And the next step, I also implemented the iterative updates, the same goes as the manual version, alongside with the identification of bit errors when storage exceeds capacity. And in the end, I stored three binary patterns for recall testing and also computed symmetric Hebbian weight matrix for associative memory. So, one thing I have to add in the interpretation of homework 19 and 20 is that what I struggled with and what I learned. Because with homework 19, we didn't get to learn it during class. It's all about self work, reading books, and reading slides. And for a person who's not familiar with math like me, it was pretty tough. And also because English is my second language, so I had a hard time analyzing all of the formulas and the theory. And with when I did the code implementation, I can tell that managing and debugging the matrix operation in NumPy, since small sign or shape errors can cause incorrect results, and I experienced that because the matrix was relatively small. But however, I learned how to uh, understand how Hopfield networks store and recall memories through iterative energy minimization, which is quite similar to homework 11, in which we also did iteration steps. And I can tell that after this, I gained a clear understanding of how perceptron make linear decision and how multi-layer architectures handle nonlinear problems, and also strengthened my skill in Python, of course, of neural models, matrix manipulation, and also debugging. And that is the end of my presentation. Thank you for watching this, and thank you for the work that you have done for us, and I really appreciate it. Thank you so much.